Good morning. Let us start morning session. And the first speaker today is Professor Yujiro Kawamata from the University of Tokyo. And title of his talk is on deformations over non-commutative base. So please start.
Thank you very much. So I'd like to thank the organizers of this conference for this great conference. And it's a great honor for me, and also very generous support for this for my trip this time. So I appreciate very much. So I think I knew Deji before I met him. I think on so I think Miyanisho yourself sent me your thesis on log surfaces. So at that time, logarithmic variety of dimension 2 was a hot topic, and so first non-negative quadratic dimension case was easily generalized from usual compact surfaces. So log surface is just a surface with boundary, and then so for negative quadratic dimension case, so people continued the investigation, and so first it was so if the boundary is contractible, so it is easier case, I think. And Miyanishi and Tsunoda made development and the existence of a cylinder and so on. But the most difficult case is when the boundary is contractible. So it is a log Del-Pezzo surface, essentially. And so he wrote his thesis on, I think that's thesis, yeah. It was quite a thick paper, and that was quite impressive. So because the calculation of the boundary is very difficult. It's just intersections of curves on the surface. So it's a very traditional subject, for example, Italian school and also Kodaira and so on. But it was a very difficult calculation, and he did this kind of calculation. It was very impressive, and so this classification of log Del-Pezzo surface is quite important topic. But it was a very difficult subject, and actually about 10 years later, so Keel and McCann continued his work, and I checked today the paper by Keel and McCann, and so his name was referred to at the biography, but with 3 different names. So maybe it was corrected in the book. The book is the memoir of AMS. Is it corrected or no? For example, one name is Chi Jan, or some D Jan, or many different names. I know that this is his name. Yeah. And at that time, so he carried out a very difficult calculation, and I remember that Takao Fujita said that Chinese is very powerful because the Chinese food is more powerful than Japanese. Yeah. So and then I think I met him in Kinosaki. Yeah. And since then I met him many times, and we made a lot of discussions, many interesting subject. So for example, once he said that in China, in southern China, there are a lot of mountains and also rivers, and so it is not like northern China. So it's divided into small pieces, and if you cross the mountain, then people speak different language. So yeah, there are a lot of interesting topics. But today I'd like to speak something on non-commutative thing. So actually, I'm not a specialist in non-commutative geometry, but still I'd like to make some remark on this topic today. So this is the topic of my talk today. So I will talk again on day after tomorrow. So today I consider deformations of sheaves and of a non-commutative base. And the day after tomorrow, I'll talk about deformation of manifolds as a non-commutative manifold. Today, so the deformation of sheaves is simpler. So I will explain some general theory of infinitesimal non-commutative deformations. So NC stands for not necessarily commutative. Okay. And then I will exhibit three examples. One is divisorial sheaves on normal surfaces. Next one is deformation of subspaces. Subspaces themselves are varieties, and in this case, I can consider non-commutative deformation varieties. But these are only the deformation of structure sheaves, so it is easier. So, and then I consider also deformation of contractions, where the fibers are one-dimensional. Okay. So this is a general theory of infinitesimal deformations. So let X be a projective variety over some field K, and let F be a coherent sheaf on X. Then the modular space M of F, so usual modular space, commutative modular space, is described as a quartz scheme, according to Grothendieck. And the local structure of the modular space is described by using infinitesimal deformation theory. This is also Grothendieck theory. So it is described in SGA using T1 and T2. T1 is extension 1 of the sheaf, and obstruction T2 is extension 2. So this is a general theory of SGA. So this is commutative theory. And these extension sheaves are actually the homology groups of some non-commutative algebra. This is so-called differential graded algebra. So I'll explain this. So let develop F into injective resolution. So I0, I1, and so on are injective modules. And then the extensions are calculated as some homology of algebra A star, and A star is the derived Hom algebra, which is a direct sum of Hom I. Hom I means Hom space of I to I star shifted by I. So this is notation in the derived category, and then so each degree I set is the direct product of the Hom set, like this. So from I to the m, from I to the m to I to the m plus I. So this is the graded algebra. So algebra structure is naturally defined as a composition of homomorphisms. So this is composition, so it is non-commutative naturally. And the differential structure is derived from the differential of the injective resolution. So injective resolution has differentials, and the differential of the endomorphism algebra is derived from the differential of I. So this is a combination of first you differentiate and then map, and then first map and then differentiate. And the difference is the differential of the DG algebra. So this is non-commutative. And And since the deformation is controlled by this differential graded algebra, so it is natural to consider non-commutative base. Actually, the base of the Vassal deformation of F is described using this DG algebra, non-commutative algebra. So it is very natural that the base of the deformation is non-commutative. Okay. So the deformation of F is described by DG algebra A star, and hence it is natural to consider deformations of a non-commutative base. So it will give additional formal structure on the commutative moduli space. The commutative moduli space is a chord scheme, and its infinitesimal structure is described by this T1, T2, but it has additional structure. So it is the variety, the moduli space as a variety is unchanged, but it has some additional formal structure on it. So this is similar, in some sense similar to the variety of minimal tangents. So it is additional structure. So the question is whether it is easily calculable or not. So Jungkook said that VMRT is easy to calculate, and this is advantage. Of course, you need some experience for that. So for non-specialists, it's not easy to calculate VMRT. And maybe this is the same. Also, this additional formal structure is quite difficult. It seems quite difficult. Actually, it's difficult. But in some sense, in some cases, one can still calculate. And I will explain this in the examples later. So this is the formal definition of the non-commutative deformation. So let Rm be an Artin local associative algebra. So it is not commutative. It is not a usual local ring, but just associative, but with unique maximal ideal M. M is two-sided ideal. And then the NC deformation Fr of F over R is a flat left R module with an isomorphism. So this is exactly the same definition as the commutative deformation, except that the base is non-commutative. And then since injective sheaves do not have any deformation because extensions are trivial, so one can deform F without changing injective modules. So each IM injective modules are unchanged, but only the maps deform. So in this way, one can describe all deformations of F. So deformations of F are obtained by deforming the differential di to di plus y. So y is an element in M tensor A1. So A1 is a degree 1 element in A1 in the DG algebra. So this shift, so y shift the degree by 1. So add degree by 1. So this is the same as D. And so if you replace di by di plus y, then you define deformation of F. So di plus y is the element in R tensor I star, and I get this complex. And usually the complex is, this is not a complex actually. So this is just a sequence of linear maps. And if the square is trivial, then it becomes complex. And also one can prove that it is exact except at degree 0 place. So di plus y square is trivial, so this is equivalent to saying that the dAy plus y square is 0. And this is called the Maurer-Cartan equation for this for the deformation of this sheaf. And in this case, the deformation of F is obtained as a kernel of di plus y. So this is a description of the deformation in the case of a non-commutative base. Okay, and then there is tangent space and obstruction theory. So let Fr be a deformation of F over R, and let J R dash R. This is an extension of the ring by two-sided ideal J, which is annihilated by the maximal ideal. And then the obstruction class exists such that the deformation Fr is extendable to over R dash if and only if the obstruction class vanish. So this is as usual. And then, moreover, the set of such extensions is the tensor of J tensor T1. So this is exactly the same as SGA. And moreover, the obstruction class is factorial with respect to the commutative diagram of extensions. So everything is very parallel and very easily proved. Okay. So there are some remarks. So there is a generalization to a multi-pointed case. So if F has a direct sum decomposition to R components, then F has additional structure F has a structure over K to the R. K to the R is a direct product ring of K. It is a semi-simple ring, and F has action of K to the R. So each component of K acts each component of F. Yeah. And in this case, one can deform F, but so semi-local ring of commutative semi-local ring is a direct product ring of commutative ring, but the non-commutative semi-local ring is not necessarily a direct product of local ring. And that is why the multi-pointed deformation is not the same of the direct product of each individual component. So there are some interactions between the components. So in this case, the extension modules are bimodules over the base ring. Yeah, and also the base ring of the deformation is an augmented K to the R ring. Augmented means that in addition to the homomorphism from K to the R to R, there is another homomorphism from R to K to the R. And the base ring has this augmentation ideal is nilpotent. So in this case, the formal modular space is a quotient of the tensor algebra of the tangent space, but in this case, the tangent over the base ring. So base ring is semi-simple ring. So this kind of extension is also very naturally done. And the second remark is that there is a more precise description of the versal algebra using the minimal A infinity algebra associated to the DG algebra A star. So DG algebra has a lot of redundancies because so differential is non-trivial, so there is kernel, and so in order to get the cohomology, you need to divide out by the kernel. So if you divide that by the kernel and then get a cohomology groups, then you lose information, and this information is recovered by considering infinity algebra structure. And on the infinity algebra, the part corresponding to the differential becomes 0, but there are higher multiplications, and that will give you the same information as the original DG algebra. Okay. So the versal R-pointed and non-commutative deformation is obtained by iterated universal extensions. So this is another way to obtain the versal family. So the versal family is an inverse limit of a tower of sheaves, and from one tower to another tower. So in order to climb the tower, you construct universal extensions, and the universal extension is given by this exact sequence. Yeah. So by iterating universal extensions, eventually you get the versal deformation. So deformation is the same as extensions in the usual language. But the point is here is that I consider extension as deformation, and then deformation is flat. So extension is usually not flat, but deformations are flat, and flatness means higher cohomology vanish, and this will simplify the derived puncta and so on. So that is main point, I think. Okay. So especially if the sheaf is a simple collection. Simple collection means that there is no non-trivial endomorphism. So, for example, simple sheaf is that the sheaf which has no non-scalar endomorphism, and this is generalization of simple sheaf. And in this case, the deformation theory is very simple. And the base algebra of the deformation is, so this is theorem 2.5. If F is a simple collection, then the tower of extension is flat over the endomorphism algebra. So the base ring is automatically given as an endomorphism ring of the sheaf. Yeah. So now, so this is a description of the versal algebra. Versal algebra is a parameter algebra of versal deformation. So let F be a this F is not good. So F was a sheaf, but this is deformation functor F. So this stands for something else. I'm sorry. Yeah. So this is functor F is a R-pointed deformation of some sheaf F. So sorry. And in this case, the tangent space and obstruction space. Suppose. So this theorem framework is more general. So in this case, things can be a little bit more general. So this is not necessarily a deformation factor of a sheaf. But suppose that tangent space and obstruction space are finite dimensional vector space, and there is versal deformation. So we know that in the case of sheaves, they are satisfied. Then there is a K to their linear map from T to dual space of T2 to the completed tensor algebra of the dual space of the tangent space, such that the versal algebra is given as a quotient algebra. So this is very general statement, and actually this is very easily proved by using the usual ring theory. Okay. So as a corollary, so under the same assumption, the base ring is a quotient algebra of a non-commutative formal power series ring divided by some two-sided ideal generated by non-commutative formal power series. So these formal power series do not have any constant term and also do not have a term of degree 1. This is general, very general structure. So the base ring of the commutative deformation is equal to, so this is a summary of what I said. So the base ring of the commutative deformation, this is the completion of the modular space at the corresponding point of the sheaf. And this is equal to the urbanization of this non-commutative versal ring. And so the urbanization is easily obtained in this way. So this is a quotient of commutative formal power series ring divided by the same polynomials, but the same polynomials considered as the commutative power series. So this is additional structure on the modular space, and this will give you some kind of distribution or something. No, not a usual distribution, but some additional structure on the modular space. Okay. So now I'd like to talk about examples. So especially in the case of surfaces, it works very well. So on the surface, I want to consider deformation of divisorial sheaves. So normal surface. So let X be a normal projective surface with only one quotient singularity of type. So this is the order of the stabilizer is R, and so 1 over R and Y8. So the action of the cyclic group, this is cyclic quotient singularity, and the action is determined by the exponent. And let F be a divisorial sheaf. So this is reflexive sheaf of rank 1, but it is not locally free. So because of the singularity, at the singularity, it is isomorphic to O minus 1. O minus 1 means that this is the ideal sheaf of one axis corresponding to exponent 1. The other axis corresponds to minus a. Okay, and I assume that the higher cohomology group of the structure sheaf vanish, and then let us develop this rational number by integers C1 to CL as a continued fraction. And then the versal deformation of F is a locally free sheaf of rank R. So the initial sheaf is reflexive but not locally free. But if you extend R times, then you get locally free sheaf. And the parameter algebra is so-called Karamazin algebra. So this is a quotient algebra of a non-commutative polynomial ring divided by some two-sided ideal generated by monomials described there. So these monomials are determined by the integers C1 to CL, and so, for example, Zj, Zk become 0 in this ring. So if J is smaller than K, so for example, Z1, Z2 is 0. But Z2, Z1 is not 0. You need to multiply more. So, yeah, like this. So this is non-commutative. The relations are not symmetric. So this is a easy case. So let X be a weighted projective space, and F is minus 1. So this has singularity at the vertex. Then the versal algebra is like this, and this is proved by using this commutative diagram of exact sequence. So that lower part is the usual exact sequence of degree d minus 1, so over p1. Degree d minus 1 sheaf over p1 has d sections. And the kernel is a direct sum of O minus 1. And take if you start with this exact sequence over P1 and then taking a cone, and then you get this exact sequence again over the surface. And then pull back this exact sequence by minus d. Minus d is a curve at infinity. And this is a so-called elementary transformation of a locally free sheaf. And then you get another locally free sheaf, which is FR. This is a basal deformation. Okay. So now I'd like to explain this deformation theory with Q-Gorenstein smoothing. So Q-Gorenstein smoothing was this was found by Kohler-Shepard-Baron at the early history of threefold geometry, yeah, and now Yonnam and it's developed more. But so and Hacking found that when there is Q-Gorenstein smoothing, then semi-stable vector bundle appear. So this theorem explains the relationship with Hacking's vector bundle to deformation theory. So let X be a projective normal surface with only one quotient singularity of type of cyclic quotient singularity of this type, and again F is a divisorial sheaf which is singular at P, like this, and then assume that the global cohomology vanishes, and assume that there is a Q-Gorenstein smoothing of X. Then the basal deformation of F, so F is a divisorial sheaf, but FR is a locally free sheaf of rank R squared times S, and this extends to locally free sheaf on the total space of the deformation. And after the base change and the shrinking of the base, so there exist maximal Koema-Corey sheaves E1 to ES on X, such that its special fiber is just a direct sum of the divisorial sheaf. The special fiber is singular, just direct sum of the original divisorial sheaf. And the generic fiber, EI times OXT, for non-trivial T, are exceptional vector bundles. And they are semi-stable also. And the Cho extended this to, actually Hacking found this in the case S is 1, and the Cho extended this to arbitrary S, and there are S mutually orthogonal vector bundles. So there are no home set. So they are quite different vector bundles. And so there are S such vector bundles. And the relationship to this basal deformation is number 4. So this locally free sheaf FR has generic fiber, which are direct sum of these vector bundles. So curly EI has special fiber, singular special fiber. But this deformation has a smooth special fiber. So special fiber is locally free sheaf. So they coincide at the generic point, but at the special fiber, they are completely different. But on the generic fiber of the deformation, they are in some sense essentially the same. So in this way, so the Vassal deformation is unique after isomorphism. So starting from a divisorial sheaf, I constructed Vassal sheaf, which is unique up to isomorphism, and also deformation is unique. So the generic fiber is unique, and by taking an indecomposable component, you get this vector bundle. So in this sense, these vector bundles are quite natural. Of course, this kind of inseparability of the moduli is quite usual phenomena. Yeah. And also, these orthogonality is interesting. Yeah? So all EI has the same special fiber. So they specialize to the same singular sheaf, but they are mutually orthogonal on the generic fiber. So they're totally different. So this is structures. And this theorem is generalized by Wozler-Teverev in the more general cyclic quotient singularities. Okay. So now I want to consider non-commutative deformations of subvarieties. So let Y be a subvariety. By the way, are there any questions? No. Okay. So if there is any question, please interrupt me at any time. Okay. So now this is a second example. This second example is a deformation of subvariety as a deformation of structure sheaf or Y. And so I consider very, very special, easy case. So this is a Grassmannian case. So I consider linear subspace Y in a projective space, and the moduli space of Y is Grassmannian. And so Grassmannian has a smooth tangent space. So there is no local structure in some sense. Of course, there is VMRT, and so the more subtle structure. But here, I will explain that this non-commutative deformation has some additional structure at the point of Grassmannian. So let V be a vector space with coordinate x1 to xn. So this corresponds to the whole projected space X, and W corresponding to Y defined by ideal xn plus 1 to xn is 0. And then the home set from W to V over W is a fine chart of the Grassmannian, and the coordinate is Aij. Okay. So this is an open subset of the commutative moduli space. And then the non-commutative moduli is given in this proposition. So the parameter algebra of the formal Vassal non-commutative deformation of the structure sheaf of this linear space is given below. So, and also the Vassal family is given below. So the parameter algebra is a formal non-commutative power series ring divided by two-sided ideal generated by these polynomials, non-commutative polynomials. So these polynomials are all commutators. So if you consider if you consider commutative polynomials attached to them, then they all vanish. So there is no equation at all. But on the other hand, not all commutators appear. So there are some commutators appear, and some. So for example, the first one is just a commutator, but the second equation is the sum of commutators. So each commutator does not vanish, but the sum vanish. And the corresponding idea is just the same. So as in the commutative case, so this is just the same as before. So on the Grassmannian. So this is formal versal NC deformation on the Grassmannian. But the Grassmannian is in some sense globally flat in some sense. So this proposition is generalized into more global statement. So this deformation is algebraic in the following sense. There is a non-commutative deformation of ideas, I tilde. So I hat was the formal one, and the I tilde is algebraic one over parameter algebra R tilde. This is a quotient algebra of NC polynomial algebra. So in this case, this is not formal, but just polynomial. But the terms are the same. Just I removed this bracket in both sides. There were two brackets for formal case, but in this case, I have only one bracket. So this is not formal. So the reason is the following. So first of all, the set of closed points of the non-commutative moduli space is the same as the set of maximal ideals. And the maximal ideal has a commutative. Maximal ideal means the residue is a field, and the field is automatically commutative. So what I get is only commutative points. So if you consider points on the non-commutative space, then you lose all the information, and just the set of points is the same as the commutative case. This is like scheme. So if you consider the set of points of a scheme, then you lose a lot of information. Also in the non-commutative case, if I consider only points, then I end up with, again, with just Grassmannian. And then at each point, the formal structure is the same because this calculation shows that if you shift Aij by Aij 0, so by some constant, then the commutator doesn't change. So the commutator, the ideal, defining ideal J tilde does not change if you shift a point. So parallel translation. So this equation is holds at every point of every closed point. So in this sense, this NC deformation is global. Okay. So this is just a stupid calculation. But for example, if you consider just one-dimensional subspace in three-dimensional space, then you get just ordinary polynomial ring. But so if you take dual and so two-dimensional space inside three-dimensional space, then what you get is non-commutative polynomial ring. So it is not even Noetherian. And from this non-Noetherian ring, by taking quotient algebra, so if you take a quotient algebra of the versal ring, that corresponds to some non-versal deformation. And there are non-versal deformations over, for example, this kind of ring, which is the same as the ring of differentials, differential operators. And you have more things. So if you specialize, then you get a lot of a lot of rings, and that means that, for example, in the last case, over the ring of two differential operators with two variables, you get deformation of two-dimensional. Line. This is line in P3. So this is not versal, just part of the deformation. So you get a lot of such deformations. So finally, this is the last section. So I want to consider contraction of curves. So this is the situation where Vandenberg considered in his famous paper on the flop and I think three-dimensional flop. In the introduction, it was written that it was first considered as a joint work with Bridgeland, but due to his laziness, he wrote this paper himself. Something this is said. So let F be a projective surjective morphism to a germ of a complex space Y, and assume that the fiber dimension is at most one for every base point. So every point on the base. And moreover, assume that there is no higher direct image sheaf, and also it's a contraction morphism. And let C1 to Cm be irreducible component of the central fiber. And let us take line bundles which intersect these curves with this Kronecker symbol numbers. And then, so these Li are ample sheaves because it is not ample. So I mean Neff line bundles. And because of this, the vanishing of the higher direct image sheaf, they all have vanishing higher direct image. So RF star of Li vanish. Higher direct image. But so if you take the inverse of Li, then the higher direct image may not vanish. So in order to kill the higher direct image, one consider this extension. So if you have R1 F star of Li inverse, then you get extension like this, and you take kind of minimum number Ri, which is sufficient to kill all the direct image sheaf. So after this extension, R1 F star of Mi inverse all vanish. So yeah, and then these Mi are locally free sheaves, and take the sum with the structure sheaf and all these Mi and called P. This is a locally free sheaf on X, and this is tilting generator in the following sense. So this is a locally free sheaf which has no extension sheaf, so except endomorphism, and moreover, for non-zero sheaf, you get always Home-set. So this is the definition of tilting generator of the derived category. And let R be the endomorphism ring of this tilting sheaf. Then there is so-called Bondar-Ricard equivalence of derived category. So phi is a equivalence from the derived category of X to derived category of right R modules. So the image on the, so on phi of A acts, so the ring, endomorphism ring R from the right by the action through P. So this is derived home from A to P, and after P, the ring R acts afterwards. So that is right action of the ring. And this is so-called tilting theory, so that's equivalent. And then we define an abelian category of perverse coherent sheaves as a abelian category corresponding to the module category. So they are derived equivalence between the derived category of X and some derived category of modules. And on the right hand side, there is abelian category of modules. So on the left hand side, there is abelian category of coherent sheaves. And this derived equivalence changes so-called T structure. So these abelian categories do not correspond. So on the right hand side, you have abelian category of modules. And if you go to the left hand side by using this equivalence, then what you get is the category of perverse sheaves. And the category of perverse sheaves is more algebraic. So the category of coherent sheaf is very geometric. So all geometric statement expressed by using coherent sheaf of X. But on the right hand side, this is a module category. So it is very, very algebraic. And so this algebraic nature is expressed in the next sentence. So the set of simple objects in this category of perverse sheaf over the central point y0 is only the set of the structure sheaf of C and the structure sheaf of irreducible component shifted by 1. So there is only finitely many simple objects. So in the geometric side on X, so if you consider the central point, then if you consider central fiber, the central fiber is the curve. So each point on the curve are the simple object. So the skyscraper sheaf on the curve are all simple objects. So there are infinitely many simple objects on X, but on the perverse side, you have only finitely many. So this is more algebraic. So original perverse sheaves is defined by Riemann-Hilbert correspondence. So on the left-hand side, you have a derived category of holonomic D modules. And on the right-hand side, so derived category of constructible sheaves. And the constructible sheaves are more algebraic, and these D modules are more geometric. And also, so the sheaf, if the complex of D module is just a sheaf of D module, then the corresponding thing is a perverse sheaf. And perverse sheaf is not a sheaf, but just a complex of sheaves. So in this way, the correspondence is very parallel. So this is why it is called perverse coherent sheaves. Okay, the theorem says that the non-commutative deformations of a simple collection, so of all simple objects. So as I said, there are only finitely many simple objects. But if I take the sum of all simple objects, and then the Basel deformation recovers the tilting locally free sheaf, and the parameter algebra is just the endomorphism ring. So this is the Basel ring. So in this way, you can recover the tilting object in the Basel ring. But if you consider only partial simple collection, for example, if you remove the structure sheaf of the curve, then you get the more interesting deformation theory. So let I be a two-sided idea generated by object of endomorphism, which is factored through the structure sheaf OX. This is one of the irreducible component of that of P. And then the Basel deformation is just a kernel sheaf of this. Yeah. So this is supported only on the locus where F is not isomorphism. For example, if you consider flopping contraction of a threefold, then it is just supported by isolated point. But it's much more general. So, yeah. And the parameter algebra is the endomorphism algebra of Q, because it's a simple collection, and this is given by the quotient of the endomorphism algebra divided by I. For example, in the case of contraction of flopping contraction of threefold, this is so-called contraction algebra of Donovan and Wemyss. Okay, I think. Yeah. Yeah. So, for example, in the case of flopping contraction, this the contraction algebra reflects the infinitesimal neighborhood of this contracted curve, and that reveals some the deeper structure of the neighborhood. So commutative deformation is it's just a usual modular space. But if you consider non-commutative modular space, then that reveals deeper structure of the modular space, and you get more information. So this is exhibited by this Donovan Wemyss results. They showed many results on flopping contraction. But this theorem holds also for flipping contractions or much more general. Just the assumption is that just fiber is one-dimensional. Oh, okay. Yeah. So maybe I have still 2 minutes. So what should I explain? Is there any question? No. Classified. No. Using this tilting object. So if you have a tilting object, then you get Hubbard structure. Yeah. Modular of T structures. This is just different opposite direction. So I don't know any classification of these structures in this case. So this T structure is usual So Fourier-Mukai correspondence is both sides are geometric. Yeah. So for example, in the case of K3 surfaces, you classified this, yeah, and so using the lattice and so on. But this is not a whole T structure. Just other K3 surfaces corresponding to Fourier-Mukai thing. And this one is similar to Mukai correspondence, and so Mukai correspondence connect geometric thing to algebraic thing. Yeah. So there are many different type of T structures. Yeah. So it's very far from the classification anyway. Yeah. 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 So this kind of thing is inspired by this. There was a paper by Bridgeland King Reed, and the original title was "Mukai implies Makai," and Mukai and Makai very sound similar. But Mukai is this geometric correspondence, and Makai is this. Yeah. So this is kind of generalization of Makai. But now it's time. Yeah.
Thank you very much. あちらに、questions or comments?
Threefold. Threefold case, yeah. Huh? 3.3. What was 3.3? What was that? This is this is on non-commutative. So you want to deform the surface itself. So in the next talk, I will explain the deformation of varieties. And so I will explain that in that case, the base ring cannot be commutative. So there is some reason. So if I need to introduce non-commutativity on the fiber, so the fiber is a variety, and the base is base ring. And if there is non-commutativity on the fiber, then the base is automatically commutative. Otherwise, there's some contradiction. Something. Yeah. Of course, if there are more than one, then still one can do something. Yeah. For example, in the case of toric surface, you have many singularities, but still you can do something. Yeah.
あちらに、
Yeah, so I did not do this kind of thing, but the framework is the same, so one can do the same thing, I think, for flipping contractions. But I don't know the result, or what will happen on that. But this Vandenberg situation is much more general, so.
Are there any further comments or questions? So thank you very much again.
Thank you.